Alright, so the second part is about chapter 13. We're going to learn about all the reactions that alkynes do and also how to synthesize alkynes. Alright, so first a bit about alkynes. Alkynes are hydrocarbons, so just carbons and hydrogens, that contain a carbon-carbon triple bond. The reactions are very similar to alkenes, and we're going to see it a lot. And much of the chemistry, a lot of the chemistry associated with also is about the acidity of the CH bond, which we talked about when we learned about acids and bases and hybridization state and how that affected acidity. One common thing people make mistakes with alkynes is they draw them incorrectly. And so I just want to show two examples. This first one is an internal alkyne because the alkyne has two carbons on either side. And this one is a terminal alkyne because this alkyne actually has an H on the end. Each of them have different numbers of carbons. 1, 2, 3, 4. 1, 2, 3. So how you draw alkynes is really important. A lot of times people will draw alkynes. I see a lot of this. So how many carbons does this actually have? It has probably more than you want. 1, 2, 3. See that little curve there? 4, 5, 6, 7, 8. So be very careful on how you draw alkynes. A lot of times it's easiest to draw the alkyne first and then draw everything else around it. Remember, alkynes have that linear geometry, so it's maybe easiest to draw the alkyne first. A couple basic stuff. Of course, an alkyne is a triple bond, so it has 1 sigma and 2 pi bonds. They react very similar. They have very similar physical properties of alkanes and alkenes. And then, of course, because they have less carbons, the intermolecular forces, the first 4 alkynes are gases as well. So sigma bond, 2 pi bonds. We're really concerned about those pi bonds when we do these reactions for these addition reactions with alkynes. All right, so our first reaction with alkynes is going to be a hydrohalogenation. So it's similar to what we've done before. So it's a hydrohalogenation. So what that means, we're doing an addition reaction. We're going to add H and X, a halogen. We're going to get, in this case, we're going to get a trans addition. And we're going to get a trans addition. We are going to form a carbocation. In the first step and the second step, the first one has no rearrangement cell. So we form a carbocation in the first step here, we don't get a rearrangement. We do get trans addition, and it's a Markovnikov type product. So let's look at this mechanism now. So we have an alkyne. So it has a terminal alkyne, so one of the carbons has bonded H, one bonded another carbon. We're going to get this H. And I would disagree with this. I would think that these would actually be trans to each other. I'll show that to you here. This first mechanism, the pi bond reacts. You get the hydrogen bonded to the less substituted carbon, breaks the HX bond, and the halogen comes back in and reacts. This carbocation, this vinyl carbocation, will not do a rearrangement. It'll add trans. So the first carbocation, no rearrangement, very similar to what we did before. We had a hydrogen and a halogen. What if we don't just have one equivalent? What if we have, so there's one HBr and then we add another HBr? What do we get then? Again, we get the same type of thing. It's again a hydrohalogenation. You are adding H and Br, so just like you did before, H and X. You're going to add them in a trans-like fashion. So you see here the first step, break the hydrogen, make a carbocation. This carbocation will not rearrange. Pi bond reacts again, breaks the bond, and we make the more stable carbocation, which in this case is the carbocation next to the bromine, because we can do a resonance, lone pair resonance stabilized system. So the bromine could either come in and react here, or you could show it doing this addition this way with 2 arrows. Either way, the bromines end up on the most substituted carbon, and they both end up on the same carbon. A lot of times this won't do a rearrangement because it's already very stabilized by lone pair resonance from the bromine. So hydrohalogenation, you add H and X, you get a trans addition, the anti-stereochemistry. And both, if you had a second equivalent, the bromines end up on the same side because of resonance stabilized lone pair resonance. So let's take a look at a reaction we've seen with alkenes. hydration of alkynes here. So hydration of alkynes is when we add hydrogen and solvent, hydrogen solvent, whatever the solvent would be. So we're going to add H and solvent. A lot of times the solvent's water. It's going to be a Markovnikov addition. We're going to go through a carbocation, but not the kind of carbocation that rearranges. So it has a carbocation, no rearrangement, so. And we're going to get that trans product, which then actually is going to end up being tautomerized. We have tautomerization here at the end, if possible. If possible. And we'll see that in a second. So the first step, let's number our alkynes, 1 and 2. 1 and 2. First step, the alkyne is going to react with the H+. Always find that H+. We're going to react with that first. We're going to form a carbocation on carbon 2, the more substituted carbon. We're going to have water, then react. So it would add trans. So if the H that we added was there, let's say this H is there now, the water adds trans. So we get the H we added, which we circled in red, the original H, methyl, and the water. Balance our charge, so now a plus charge on there. All right, at this point we're set up for a tautomerization. And so we can take the pi bond, take those there, make a new pi bond there, and that will give us a ketone now, and we've regenerated H3O plus, or we still have water floating around, sorry. We still have water floating around, so the 3 H's have been added here. We keep track of our carbons. This was carbon 2, this is 1, carbon 2, carbon 1. And the final step, water will just take that H, and we'll get the final ketone in the final step. It's a little different with solvents like methanol, though. So first steps are the same. Grab that. First step's going to be the same. Grab that H. We're going to make a carbocation. That's not going to be able to rearrange, just like before. Get that trans addition. So I'll circle in blue this time the H we added. There it is. In our solvent, we're going to add methanol. So the oxygen's lone pairs are the nucleophile. Next there. Now we get is that H? There should be a plus charge on this oxygen. All right, and we number our carbons 2 and 1, 2 and 1. Now at this point, actually, H plus could just fall off, regenerate H plus, and that will actually just give us something that's stuck. We can't do a tautomerization with this because there is no H's left on that oxygen, and so we're left with H plus. We've regenerated our catalyst. Right, shown here. That green, those fell off. H plus, lost electrons. There's carbon 2. There's carbon 1. We have this ether we formed, but another possible product. But this can't undergo tautomerization because, unlike up here, there is no OHs left on there. So this is a hydration of alkynes. Tautomerization, if possible. You've seen. You get the trans addition, carbocation, but there's no rearrangement with this type of carbocation. You get the Markovnikov addition, and you're adding H and solvent.